Our goal for the next couple of lectures will be to better understand entanglement, and density operator is the tool to do that. So imagine that we have a beam of elementary particles, possibly in different quantum states. So when we perform a measurement, so this beam may split into several sub-beams corresponding to eigenstates of the observable. Right, so here we perform a measurement. So density operator will tell us what are the intensities of the corresponding sub-beams given the observable, but it will do so without telling us what are the precise states of the particles in this beam. So this means that this density operator is capturing some statistical information about the whole beam without specifying individual states of the particles in this beam. A beam of particles is called pure if all particles in this beam are in the same quantum state. And we shall begin with this much simpler case. So let's consider that all particles in this given beam are in the same quantum state, so this beam is pure. Let us recall the mathematical model for the process of measurement. Mathematically, to each measurement, we associate an observable. So this is a self-adjoint operator. So let's call it A on the space of states V. We know that every self-adjoint operator is diagonalizable. So we can say that A has an orthonormal basis of eigenvectors. Say V1 through Vn with real eigenvalues lambda 1 through lambda n. Now, what happens when we apply this measurement to a particle in state V or in state W in the space of states V? Right, so this W is, of course, a unit vector. To find out the probabilities of observing values lambda 1 through lambda n, if we start with the state W, what we have to do is we have to expand W in the basis of eigenvectors. So we need to write down W as C1 V1 plus Cn Vn. If we have this expansion, then the probability of measuring lambda j is equal to the norm of coefficient Cj squared. And of course, because norm of W is equal to 1, so this translates into the fact that norm of C1 squared plus norm of Cn squared, so this is equal to norm of W squared, and so this is equal to 1. So this tells us that the sum of these probabilities is indeed 1 as it should be. Now, how can we find these coefficients? Well, there is a simple trick to it. So what we do is we take the scalar product, Hermitian scalar product of W with one of the basis vectors Vj's. So what will this be? So this is going to be Vj with, and so here we input this linear combination C1 V1 plus Cn Vn. And so that equals to the sum, k goes from 1 to n. So by linearity we get Ck times Vj with Vk. But what we have here is that we know that this basis is orthonormal. So this means that these scalar products are equal to 0 unless k is equal to j. And when k is equal to j, so this value of the scalar product is equal to 1. And so what we get is that this sum will contain only one non-zero term, namely the one when k is equal to j. And what we get is we get Cj times Vj with Vj, which is equal to Cj. And so this tells us that to find the coefficient Cj of this expansion, all we have to do is we have to take the Hermitian scalar product of a given vector with the corresponding vector from the orthonormal basis of eigenvectors. If instead of a single particle in state W, we have a pure beam of particles in the same state W, then the meaning of these coefficients Cj's will be the intensities of these subbeams, or rather the intensities are going to be this norm of Cj squared. When we are finding the expansion of W in the basis of orthonormal vectors V1, Vn, we're essentially computing projections of W to each basis vector. So let's recall the definition of orthogonal projection to a unit vector V. So here, we have a unit vector V and some vector W. Well, so the orthogonal projection is the projection of vector W to the line of V. So this will be projection of W onto the line of V. How do we calculate this projection? Well, first of all, we say that projection of W onto a line of V is some multiple of a vector V. And second property of the projection is that vector W can be written as the projection of W plus another vector which is perpendicular to V, so plus vector U. And so this one is perpendicular to V. Now, using this, we can find this unknown scalar C. So what we do is, we take scalar product of V with W. So what is this? So this is going to be V with, so for W, we expand this projection as a projection plus orthogonal component, and projection is equal to CV plus U. And so this is equal to CV with V plus V with U. But the vector U is perpendicular to V, so this means that this is equal to 0. And the vector V is a unit vector, right? So this means that this Hermitian scalar product of V with itself is equal to 1. And so what we get is we get that the scalar product of V with W is equal to the constant C. So this is how we can find this constant. So this gives us a formula for the projection to a unit vector V. So we can write that projection of W to V is equal to C, which is equal to V with W, times this unit vector V. So we also consider the projection operator. So which is a linear operator from our space of states V to itself. Right? And this projection operator will take a vector W and map it into the projection of W onto the vector V. Using physics notations, we can write this projection operator as ket V times the bra-V. Now, what does it mean? So this means the following, that this means that P applied to any vector W, right? And so we use, again, physics notations and write vectors as kets, right? So this is, by this formula, so this is going to be ket V times, and so here we write bra-V with ket W, right? So this is a purely symbolic trick. And what we get here is, here we see that this bra-V and ket W will form a Hermitian product. And what we get is, we get this Hermitian multiple of the vector V. And so what we see is that this formula is actually identical to the formula for the projection that we used here, right? So this is how one should read this notation as an operator on a vector space V. In order to familiarize ourselves with these notations, so let us see how this works for matrices. So suppose we have an operator given by some matrix A with matrix entries aij's. So what does it mean? So this corresponding operator will send a basis vector ej into the sum I goes from 1 to n aij times ei. And so then what we do is we are going to write A in this ket bra notation as the sum over ij from 1 to n of aij, and so here we put ket ei times bra ej. Let us verify that these two notations are consistent with each other. So let's see what will happen if we apply A to the basis vector ek. So by this formula, so this is equal to the sum ij, aij times ei with ej and coupled with ek. But the basis of ei's is a standard basis, and it's orthonormal. So this means that this is equal to 0 whenever k is different from j, and is equal to 1 when k is equal to j. And so the only term that will survive is when j is equal to k. So what we get is we get the sum over I from 1 to n. So j is equal to k, so we get aik times ei. And what we see is that this is in total agreement with this formula. So we see that EK goes to sum over I, AIK, EI. So just as we have here. So this means that these are two different notations to write the same operator on the space V. One more point about this notation that we will be using later is about the trace of the operator. Right? So the trace of an operator is the sum of diagonal entries. So that is the sum over I from 1 to n of AII. But what we can see is that this can also be written as the sum over I and j, AIJ. And here what we do is we switch the order of these two. So we put EJ with EI. Right. So if we have operator written in this ket bra notation, then in order to compute its trace, all we have to do is we have to switch this ket and bra and write down bra-ket. And so then this becomes a number, right? So this number here is equal to 1 when I is equal to j. And then this will give us the sum of diagonal terms, and which is the trace of an operator. So now we give a definition. So for a pure beam, in a quantum state W, the density operator is the operator of projection to W. So this is going to be P, which is W times W. Right? So here we, of course, assume that norm of W is equal to 1. For a non-pure beam, the density operator is the average of the projection operators. So rho is equal to, so suppose we have capital N particles. So then we take I goes from 1 to n, and we have Wi times Wi, where these are, so Wi's states of particles in the beam. So let us study the properties of the density operator. Well, so first property is that orthogonal projections are self-adjoint. So what does it mean? So this means that for all vectors v and u in the space V, So we have the following equality, that V with projection to W of U is equal to projection of W of V with U. Let's compute the left-hand side. So here we have V with projection of U to W. So by our formula, so this is equal to V with the scalar product of W with U times W. And by linearity of Hermitian product, so this is equal to W with U times V with W. Now, let's compute the right-hand side. So for the right-hand side, we have projection of V to W, scalar product with U. So this is equal to, so by our formula, so this is going to be a scalar product of W with V times W. So, and this is with U. So now the Hermitian scalar product is sesquilinear. So when we take this out, so this comes as a complex conjugate. So this becomes W with V complex conjugate times what's left, the scalar product of W with U. And now this we can get rid of this complex conjugation by switching the order of terms. So we know that this is equal to V with W times W with U. And so what we see is that the left-hand side is equal to the right-hand side. And as a corollary, we get that density operator rho is self-adjoint, because, well, in the pure case, the density operator is the orthogonal projection operator, and thus it's self-adjoint. Or in non-pure case, it's an average of self-adjoint operators. But a sum of self-adjoint operators is again self-adjoint. So what we get is that the density operator is self-adjoint. Now, let's consider again an observable A. So with an orthonormal basis V1 through Vn of eigenvectors with eigenvalues lambda 1 through lambda n respectively. So what we claim is that in our new notations, A can be written as a linear combination of projections. So A can be written as the sum I goes from 1 to n, lambda I times Vi times the bra-Vi. Right? Or, so this is the same as the sum I goes from 1 to n, lambda I times projection operator to Vi. Now, how can we verify this property? So it's sufficient to check that this operator A does the right thing in our orthonormal basis. So what we can do is we can apply A to the vector vk by this formula. So here, so this is I goes from 1 to n, lambda I, vi times vi with vk. But this is 0 when I is different from k, and 1 when I is equal to k. So out of this summation, only one term will survive, namely the one where I is equal to k. And so what we get is that we get lambda k times vk, and here vk with vk is equal to 1. And so what we see is that when we apply A to vk, we get lambda k times vk, that indeed the result is the one that we expected, because here we had the eigenvectors, so this means that A applied to vk is supposed to be equal to lambda k times vk. And since this operator does the right thing in the basis, so this is the correct operator. And now let's state the proposition. When we perform a measurement with observable A on a beam with a density matrix ρ, the intensity of a subbeam corresponding to observed value lambda k is so norm of ck squared, which is equal to trace of ρ times the operator of projection to vk. And part 2 of this proposition is that trace of ρ times A so is equal to the sum k goes from 1 to n lambda k times ck squared. And physically, this is interpreted as the average observed value. So this proposition tells us that the density matrix incorporates all statistical information about the beam. So it predicts the intensity of each subbeam corresponding to each value. So it can be computed using the density matrix and the projection operators. And also, if we take the trace of the product of the density matrix times the observable operator, then this gives us the average observed value as the outcome of this measurement. So let's give a proof of this proposition. Well, first we know that it is sufficient to consider a pure beam, because if we can prove this for a pure beam, then for non-pure beams, the result will follow just by averaging over all states in this beam. So we can see the pure beam with state W, where norm of W is equal to 1. Then, so let's look at the left-hand side and at the right-hand side. So what was the coefficient ck? So the coefficient ck was the coefficient of expansion of W in the basis V1 through Vn, right? And this was the coefficient at Vk. And so we had the formula for this, that Ck was the product of Vk with W. Now, let's compute the right-hand side. So for the right-hand side, so we have trace of the product of rho with projection to Vk. Now, and rho is the operator of projection to W. Right? So here we have the trace of the product of two projections. So now, so the first operator is the ket W times bra W. And this, we take the product with ket Vk times bra Vk. And so here in the middle, we already get the scalar term, right? And so here we have another ket and bra. And what we said is that when we compute the trace of an operator, which is written in this way, all we have to do is we have to switch the bra and ket. So this means that, so this becomes, so W with Vk times Vk with W. And now let's compare it with our formula for Ck. So here we see that the second term is precisely Ck. And the first term is the complex conjugate of Ck, right? So because when we switch the order of terms in the Hermitian product, we have complex conjugation. So what we have is we have Ck bar times Ck, which is norm of Ck squared. And that's exactly the claim of our first part of this proposition, that the intensity of the subbeam that corresponds to eigenvector Vk is the trace of the product of the density matrix with the projection operator to Vk. Now, to prove the second part of this proposition, so we start with trace of rho times the observable A. So this is trace. So for the pure beam, the density matrix is projection to W. And now, so we write this as trace. So the projection to W is ket W times bra W. And A, as we mentioned, so can be written as the sum I goes from 1 to n, lambda I times ket Vi times bra Vi. So now, so this becomes trace of the sum I goes from 1 to n. So here we have W with, well, we can put lambda I here, times W. So then bra W with Vi times Vi, like this. Right? And so then, just as we said before, so to compute the trace, all we have to do is we have to switch the order of this bra and ket. So then this becomes the sum I goes from 1 to n, lambda I times W with Vi times Vi with W. But that's exactly what we had in the previous computation. So what we see is that this term is equal to ci squared. So what we get is we get that sum I goes from 1 to n, lambda I times norm of ci squared. And so these is the sum of observed values weighted with probabilities of observing the corresponding values. And so this means that the physical meaning of this sum is the average observed value as the result of this measurement. So we introduced density operator rho, well, also known as density matrix. In the context of beams, or in particular non-pure beams. So this density matrix encapsulates statistical information about the behavior of a non-pure beam with respect to any possible observable. But it turns out that there is a second situation where a density operator can be introduced, and it's in fact very useful for studying entanglement. Right? So here, we will look at entangled or bipartite quantum systems. So let's talk about density operator in this context. Right? So what we have is so the setup is the following. So that suppose we have an entangled pair of particles, and so this pair flies into different directions, and we have two locations. So we have one location, say, let's call it A, and another location B. Right? And suppose we can perform, so we can only perform measurements at location A. So how can we describe the density matrix that will predict us statistical properties of outcomes of local measurements in location A? Now, so mathematically, so what we have is if we have a pair of particles which is entangled, then the state of such a particle belongs to the tensor product of the spaces corresponding to the parts, right? So this, so we can think that we have one space V associated with location A, and another space W associated with location W, and so then if we have a general entangled state, then this will be unit vector in the tensor product space. And so this state can be written as the sum over I goes from 1 to n, where n is the dimension of V, and the sum j goes from 1 to m, where m is the dimension of W, and so here we have Cij times Vi tensor with Wj. Right? So this is how we write the general entangled state for such a pair. Now, so we give the definition that density matrix rho V of state psi in V tensor W is defined as, so rho V as the trace in space W of the projection operator to the state psi. So this means that this is psi times psi. Now let us work out this expression. So we have rho V equals, so trace in space W of, so we write down psi, so we write down this expression, sum over ij Cij times Vi tensor with Wj times, so now we have to write down bra of psi. And remember that when we go from column vectors to row vectors, we take the transpose and the complex conjugation. So I will use different symbols. So here we'll put the sum over Ks. So we have Cs, and we have to take a bar because we take the conjugation, times the bra Vk tensor with bra Ws. And so now we're taking the partial trace. So we take the trace in the space W. So this means that we switch the order of these two terms. So we get the sum in Ij, the sum in Ks. We have Cij with Cks bar. And we have so Vi times Vk. And here we take, so times Ws with Wj. And so this basis is assumed to be orthonormal. So this means that this is non-zero only when S is equal to J. And so what we get is we get sum over I, J, and K. So Cij times Ck, well, S must be equal to J bar, times Vi times Vk. So here, if to this entangled state we associate a rectangular matrix C, so which is the Cij, then what we see is that here we get operator with the matrix. So we get rho A is operator on V with matrix which is the product of this rectangular matrix C with its transpose conjugate. Right? So then if we consider this product, then this will precisely give us the entries that we have in the operator rho. Now let's consider some examples. So suppose we have the following state psi in a bipartite system. So it's 1 over square root of 2, so 0, 0, plus 1 over square root of 2, 1, 1. Here we have a 2 qubit, which is a tensor product of 1 qubits. And so then what we want to do is we want to compute the density matrix that corresponds to the first component. So this density operator is going to be the trace over W of so psi with psi And so this is going to be trace over W of, so when we write the first psi, so it's just this vector, 1 over square root of 2 times 0, 0, plus 1 over square root of 2, 1, 1, times the corresponding bra, right? So we take the transpose and conjugate. So here the coefficients are real, so there is no issues with conjugation. So we get 1 over square root of 2, and now we take the transpose 0, 0, plus 1 over square root of 2, and here the transpose is going to be 1, 1. And now when we multiply this and we take a trace in W, so we're looking for matching second components. So when we take the trace, so 1 over square root of 2 times 1 over square root of 2 will give us 1/2. So we have matching second components here. So this becomes 0 times 0. Plus, well, here they don't match, here they don't have match, and here they match. So plus 1 over 2, and we have 1 times 1. And so we see that in this case, the density matrix is the diagonal matrix. So it transforms 0 into 0 and 1 into 1. And the coefficient is 1/2. So this is the density matrix that corresponds to this quantum state. So let's consider another example. So let's take psi to be 1/2 0, 0 plus I over square root of 2 times 0, 1 and minus I over 2 times 1, 1. Right, so we can note here that norm of this psi is equal to 1. So then, so what is the corresponding density matrix that corresponds to the first bit? So this is going to be the trace in the second bit of, so psi, which is this, 1 over 2, 0, 0 plus I over square root of 2, 0, 1 minus I over 2, 1, 1 times the bra psi. So here we take the transpose and complex conjugate. So this means that we get 1/2 0, 0. And now when we take complex conjugation, this I becomes negative I. So minus I over square root of 2. We have 0, 1. And so because of this I, so this becomes plus I over 2, 1, 1. And now we expand this and take the trace in the second component. So this means that we're looking for matching second components. So this equals. So here they match. So we get 1/4 0 times 0. Then here they don't match, and here they don't match. So now with this term, so 1 with 0 they don't match. So here they match. So we get I times minus I is equal to plus 1. So we get plus 1/2. And the first components will become 0 times 0. And so here we also have matching components. So I times I is equal to minus 1. So minus 1 over 2 root of 2. And we have 0 times 1. And so here these do not match, and these do match. So we get minus times minus will give us a plus, but I squared will give us a minus. So minus 1 over 2 square root of 2. And so here we have 1 times 0. And finally here we get plus 1/4, 1 times 1. And now we can write down the corresponding density matrix. So when we collect these two terms, so we get 3/4. And so as an operator, this is an operator that sends the first basis vector 0 into the first basis vector 0. So this corresponds to this entry of the matrix. Then, so this term sends the second basis vector into the first one. So what we get is, we get here we have coefficient minus 1 over 2 root of 2. And this term sends the first basis vector to the second one. So this entry sits here. And finally, so this 1/4 will belong here, right? And so what we see is that this is the density matrix that corresponds to this state psi, well, with respect to the first component. Now, let us state our main theorem about density matrices. So, theorem, so this is properties of a density matrix for bipartite quantum systems. So let rho v be the density matrix for a state psi in the space V tensor with W, and norm of psi is equal to 1. Then we have the following properties. 1. Rho v is self-adjoint. 2. Rho v is non-negative, meaning the following, that for every state phi in the space V, the following expression is real and greater or equal to 0. 3. Trace of rho v is equal to 1. 4. Eigenvalues of rho v are non-negative real, and add up to 1. 5. If psi is unentangled, then rho v is a projector operator, a projection. And has rank 1. And finally, part 6. So if A is a local observable on the space V, right? So remember that psi is in the tensor product, right? So when we perform observation just on V, so then really what we mean is that the observable is A tensor identity on B, right? So this is an observable that corresponds to a self-adjoint operator on V, and so this operator does nothing on the space W, right? So then, in this case, the average observed value on the state psi is the trace of rho times A. So what we see from this theorem is that the density matrix for bipartite quantum systems has very similar properties to density matrices of non-pure beams. And in particular, so this shows us that we can extract statistical properties of local measurements in the space V from just the density matrix. But there are also additional properties that are related to entanglement. So here, so an important part 5 says that psi is unentangled, then the density matrix has rank 1. So this gives us a way to capture or distinguish entangled states from unentangled states through the density matrix. Now let us give a proof of this theorem. As we have seen, so we can write down the density matrix as the sum over ij and k, Cij times Ckj bar times Vi times Vk. We know that a matrix is self-adjoint if it is equal to its own conjugate transpose. So let's compute the conjugate transpose of this matrix. So this will be the sum over ij and k. So here we take the conjugate. So Cij times Ckj bar and then bar on top of that. And so here we take the transpose. Well, the transpose of the product is the product of transposes in the opposite order, right? So what we're going to get is we get Vk, right? So this is the transpose of the second factor times the transpose of the first factor. So this is going to be Vi. And this becomes the sum over ij and k, Cij bar times Ckj times Vk times Vi. And what we see from here is that if we now change the switch index I with index k in this summation, then this expression will become equal to this expression here. And so what we get is we get rho V. And so this shows that this density matrix is equal to its own conjugate transpose, and so this means that it is self-adjoint. To prove the second property, we recall that the density matrix can be factored as C times C bar transpose. Well, it's essentially this factorization here. And then this expression becomes, so this is phi times C bar transpose times phi. And so here, so this factor we can put in the first one. And so then what we can see is that this is equal to C bar transpose applied to phi with C bar transpose applied to phi. Right? so here we take this second factor and apply it here. And remember, in the definition of Hermitian product, so for the first factor, we take the bar conjugate, right? So this is phi bar transpose times C bar transpose times phi. And if we work out what we have in the right-hand side, so we get the same thing. So this will be C bar transpose phi, and then bar transpose times C bar transpose phi, right? And when we expand this, we see that these two things are equal. But here we take the Hermitian product of a vector with itself. And so because of this, this is greater or equal to 0. And so this proves the second property of this theorem. So let us show that the trace of density matrix is equal to 1. So we compute the trace of rho v, and so this becomes, using this presentation, this becomes the sum over I, j, and k of Cij times Ckj bar. And then to compute the trace, we switch the bra-ket. So we get Vk with Vi. And so this basis is orthonormal. So this is equal to 1 when I is equal to k and 0 elsewhere. And so this becomes the sum over Ij of Cij times, well, k must be equal to I, Cij bar. And so that is the sum over Ij norm of Cij squared, right? So, but recall what was our psi. Our psi was the sum over Ij, Cij times Vi tensor with Wj. And so what we see is, what we have here is just the norm of psi squared. And by definition, our state had norm 1. And because of this, the trace of the density matrix is also equal to 1. Now, the property 4 now follows from what we said before, right? So the density matrix is self-adjoint. So this means that it is diagonalizable. It has an orthonormal basis of eigenvectors, and the eigenvalues are real. So now, to show that these eigenvalues are non-negative, so we take one of the eigenvectors, say, so suppose rho v times u is equal to lambda u. And then we apply the positivity property. So we know that u with rho v with u is greater or equal to 0. But what is this? So this is equal to u bar transpose times rho v applied to u. And so rho v applied to u is lambda u. So this is equal to lambda times u with u. And because this is greater or equal to 0, so this implies that lambda is greater or equal to 0. And so what we see is that the eigenvalues of the density operator are non-negative. And we know that the trace of a diagonalizable matrix is equal to the sum of its eigenvalues. And because the trace is equal to 1, so we conclude that eigenvalues of the density matrix add up to 1. So what we see is that density matrix has eigenvalues between 0 and 1. And so the sum of these eigenvalues is equal to 1. So let us look at property 5, when psi is unentangled. So if psi is unentangled, so this means that it can be written as a single tensor product of two states. All right, so we have, so V is in the space V, and W is in the space W, and both vectors have norm 1. And in this case, the density matrix is very easy to compute, right? So this is going to be the trace in W of psi times psi. And so this is trace in W of V tensor W times the bra-V tensor the bra-W. And when we take the trace in W, so these two things will be paired together. So this is equal to V times, so W with W times V. And so this term is equal to 1. So what we get is V times bra-V. And so this is nothing but a projection operator to vector V. But so this projection operator sends every vector to a multiple of a vector V. So this means that the image of this operator, so it sends all of V into one-dimensional space. And from here, what we see is that the rank of rho must be equal to 1, because the rank of a matrix is equal to dimension of its image. And as a corollary, we get that if rank of the density matrix is not equal to 1, then this implies that the state is entangled. And so now, so this gives us a way to see which states are in fact entangled. Now let us address the last part of this theorem. So what's the average observed value with respect to a given observable? So this is the sum over I, lambda I, times norm of the projection of our state psi to Vi, right? And so what we can see is that this is equal to psi A psi, right? So this is follows from the fact that A is equal to the sum over I of lambda I times P Vi, right? So from this expansion of A as a sum of projection operators, so we can get this. So here, what we need to do is we need to establish the equality that this trace of the product is equal to psi with A with psi. So this is the average observed value. Now let us establish this equality. So we have that psi is the sum over ij, Cij times Vi tensor Wj. And rho V is sum over ij and k, Cij times Ckj bar Vi times Vk. And finally, we can write operator A as the sum over Sm, A Sm times Vs times Vm. And this operator is self-adjoint, so this means that ASM is equal to AMS bar. So let's start with the right-hand side. Psi, A, psi. So here in the first sum, we take, so sum over, let's change the index of notations. We put PQ, C, PQ. Now here we take transpose and conjugate. So this is bar times VP tensor with WQ times, so A applied to psi, right? So this will be the sum over SM, ASM, and so VS times VM and times psi, sum over IJ, CIJ, VI, tensor with WJ. Now, this equals. So here, when we apply this operator to this one, right? So we have a coupling between these two vectors. So what we see is that this is non-zero when m is equal to I. So what we get is the sum over PQ, CPQ bar times VP tensor with WQ times the sum over S, so M will disappear because M will be equated to I, ASI times VS times sum over IJ, CIJ, and then all we have left is WJ here. So then here we are taking, so this WQ pairs with WJ, right? So we get non-zero term when Q is equal to J. And so this VS will pair with VP. So this means that P will be equal to S. And so what we get is that we get the sum. So the surviving indices are I, J, and S. C bar S J times A S I times C I J, right? And so this is the expression that will survive, and so this sum is equal to this Hermitian product. Now let us compute the left-hand side. So we have trace of rho V times A equals, well, rho V is equal to this. So we have trace of sum IJK CIJ times CKJ bar times VI with VK times A. So this will be sum over SM, ASM times VS times VM. Now, so here we have this coupling here. So this tells us that S must be equal to K. And remember, when we take the trace, we switch these two. So this means that we need to couple these terms as well. So M will be equal to I. And so then what we get is that this trace is equal to the sum IJK CIJ times ckj bar times A, and S is equal to K, and M is equal to I. And we see that we obtain exactly the same result after renaming S with K. So we get Cij times Csj bar times ASI. So this means that the left-hand side is equal to right-hand side, and this proves this formula.